In this example, we want to look at a physical situation, model it with a differential equation, and then use that to give us information about the actual physical problem we're looking at. In this case, we're trying to do multiple runs of an experiment that involve adding dye to a tank of water, and we need to flush the tank out with clear water before we restart again. So at the end of the experiment, we've got 2 grams per liter of dye in our 100-liter tank. We're going to add in water at a rate of 3 liters per minute to clear it. That's going to be clear water with no dye in it. And we're going to remove the water from the tank at the same rate. So I want to write the differential equation and then solve it and use that to tell me how long it will take to get down to 0.5% of the initial value. So if we draw a sketch of this situation, we have our well-mixed tank here. It contains 100 liters. We know we are going to add in pure water at a rate of 3 liters per minute. And so we're going to have an outflow as well at 3 liters per minute. We know the concentration of dye in the input stream is 0. And the concentration in the output stream is the same as the concentration inside. So if I let Q be the number of grams of dye that are in this tank at any given time, then the flow rate out will have the same concentration as what's inside, which is Q over 100, because the volume here is fixed at 100 liters. So out here we have Q over 100 grams per liter as the concentration being removed. So if we're going to let Q be the amount of dye in grams in the tank, then how does this Q change? Well, we'll have that the rate of change of Q is the rate in minus the rate out. Well, the rate in is 0. In essence, it's 0 grams per liter times the 3 liters per minute for the inflow stream. So in this case, we're really not adding dye to the tank at all, which we're not doing best in the problem either. Then how does it get taken away? Well, it gets taken away via the outflow, which has a concentration of Q over 100 times the flow rate of 3 liters per minute from the outflow. And notice that for both of these, the total units on each term is grams per minute, which is the important thing here. That is the rate of change of the mass of dye in the tank. That gives us our differential equation here. We have dq dt, or q prime, equals negative 3 over 100 q, or you could write this as q prime plus 3 over 100 q equals 0. And what's my initial condition? Well, here, we started with 2 grams per liter in a 100-liter tank. That means I have 2 times 100, or 200 grams total. So my initial condition is that Q of 0 is 200. So there is the differential equation that governs this situation. Now we can try to solve this. We can either use separable equations, this is separable, or first-order linear. I'll stick with first-order linear here. And with that method, we have an integrating factor, mu of t as e to the 3 over 100 t. The equation then becomes e to the 3 over 100 t times q prime plus 3 over 100 e to the 3 over 100 t times q equals 0, because 0 times that function is still 0. This here is e to the 3 over 100 t q prime, 0 by the product rule, which means I then end up with e to the 3 over 100 times q equals a constant, or by isolating q, my final solution here, q of t, will be c times e to the minus 3 over 100 t. And based on the fact that we want q of 0 to be 200, that means I need c to be 200 because the exponential part goes to 0, meaning my solution to the initial value problem is q of t is 200 e to the minus 3 over 100 times t. Now, to answer the actual question here, the last part asked, how long do I have to wait until the concentration gets below 0.5% of the initial value? Well, that's 1 out of 200 of the initial value, which means I want to wait till the amount of dye in the tank gets down to 1 gram. So we just solve for t once we plug that in. So I want 1 gram to equal 200 grams times e to the 3 over 100 t, minus sign there, and I just solve for t here. So 1 over 200 equals e to the minus 3 over 100 t. Get the log of both sides. Natural log of 1 over 200 equals negative 3 over 100 t. So then t equals 100 over 3 with a negative sign times the log of 1 over 200, which is the same as 100 over 3 times the natural log of 200, which comes out to about 176.6 minutes, which if you wanted to get an estimate, this is right around 3 hours. So that's a long time. If you plan to run multiple experiments in a single day, that might be too long. How could you change that? Well, if you look at the way this was set up, this 3 here is our flow rate, which is the same as the 3 here. This 200 was our starting condition value, so we can't really change that. We can't really change the 100, but the 3 we could change. And so if you say increase the flow rate to 6 liters per minute instead of 3, you've now cut this time in half. And so these modeling problems you usually answer like this, you can then see, okay, if I wanted to get this down to an hour, what do I have to make my flow rate? You can answer questions like that as well once you can solve these sorts of problems. So that's how you can approach these models, set up the differential equation to model them, and then go about solving the equation and answering questions related to the physical problem using that differential equation model.